Welcome back, Chemistry 30. This is Unit 4 and the first booklet, 17.1, a model for reaction rates. So it looks at pages 529 to 535 in the text. We'll be looking at what a reaction rate is, looking at collision theory, activated complex, transition state, and activation energy. Suggest some ways in which a chemical reaction can be measured. Calculate average rates using experimental data. Relate rates of a chemical reaction to collision between reacting particles. Discuss what is meant by threshold energy. Interpreting reaction pathway diagrams and considering the existence of transition states and activated complexes. So in general, to figure out the rate of something, you're comparing a change in some quantity over change in time. If this had been speed, we'd be looking at change in distance over change in time. But since we don't deal with distances in chemical reactions, we're looking at some change in a quantity, whether it's reactants getting used up or products being produced, gas being produced, etc. And I kind of asked the same question here again. What is the equation? We already talked about that. So that change in quantity, it's a change in concentration of reactants or change in concentration of products of some kind. So that's what the square brackets imply. And of course, if we're looking at reactants are getting used up. So a final reactant minus an initial reactant will give us a negative. So to avoid having a negative sign show up with reaction rate, we put a negative sign in front of the change in reactants. If we're talking about our quantity being a reactant, we put a negative sign in front of it so it turns out to be a positive. If we're expressing reaction rate in terms of a product, we don't have to worry about it because products are being produced. The final amount will always be bigger than the initial amount, so you always get a positive number. So if we look at, for example, this, A going to B, reactant A forming product B, we of course know that A is going to decrease in value, A is increasing in value, so we set it up like this. The rate can be expressed as A if we put a negative in front, the change in A over T with a negative to ensure that we always have a positive number, or if we express the rate in terms of B, it's just simply change in B over change in T, with no negative because it's going up in value. So if you look here, in the gas phase reaction, iodine plus chlorine yields iodine monochloride. So if we have iodine going from 0.4 at time 0, going to 0.3 at time 4 minutes later, what's the rate in terms of I being used up? Since I is a reactant, we're going to have to use that negative sign. So the negative of the change in iodine over change in T. To figure out a change, we must have had an initial and a final, and we subtract the two, final minus initial, 0.3 minus 0.4. So you can see we're going to get a negative here. And if we apply that negative out in front, it turns out to be a positive. So we get negative 0.1 over 4 minutes, and our answer works out to be decimal 0.250 molar per minute. So that tells you how fast iodine is getting used up. If you look at another one here, hydrogen peroxide being decomposed. This automatically happens when you open up a bottle of hydrogen peroxide. It starts to break down into water and oxygen. So we have a little lab here. After 20 minutes, you can see the concentration decreasing. And basically just looking at what's the rate here, 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 here. So looking at the first rate going from 0 to 2, our reactant goes from 2.5 to 2.12. So T2 minus T1 is on the bottom. 2.12 minus 2.5 is on the top. And we have to use a negative because hydrogen peroxide is a reactant. So when we do that, we should get a positive number. We do 0.19 molar per minute. So the rate is decreasing by 0.19 molar per minute. So figure out the rate from 2 to 5, then the rate from 5 to 10, then the rate from 10 to 20. You may want to pause the video and just try that out, and then look at the video again and see how you made it out. Okay, so pause it right now. Okay, if you had a chance to pause the video, here are the answers for the remaining parts. So going from 2 to 5, that's going to be 5 minus 2. And our concentration goes from 2.12 down to 1.82, so final minus initial, 0.10 molar per minute. And the last two, I just simply wrote down the answer, figuring it out. We get 0.07 molar per minute and 0.05 molar per minute, respectively. Okay, next one. Put a star beside this. I could ask you this again, hint, hint. How would the rate of the reaction, hydrogen plus oxygen yielding water, stated as the consumption of hydrogen compared to the rate of oxygen being used up? Now, if you look here in the equation, it's a 2-to-1 ratio. I need 2 molecules of hydrogen for 1 molecule of oxygen, or 2 moles of hydrogen for every 1 mole of oxygen. So it's always a 2-to-1 ratio. Therefore, we'd expect that the rates would be 2-to-1. Since H2 and O2 combine in a 2-to-1 ratio, the rate of hydrogen would be twice as great as the rate of oxygen being used up. So if we actually figured out the rate with experimental data, we would see that hydrogen's rate is 2 times bigger than oxygen's rate because they combine in a 2-to-1 ratio. So, move with that, looking at how to figure out rate, we'll look at things that cause rates to be different numbers. So first of all, we deal with collision theory. The first statement there is not that we don't talk about collision theory, it's that reactants must collide. Obviously, for collisions, you need things colliding. And the key point to go with that is that you also need to have them collide the right way, so the correct orientation, and also have the sufficient energy. And I use a demo derby as an analogy. If you want to win a demolition derby, chances are you're going to be backing your car up because you don't want your motor smashed, but you want to smash other people's motor, so you want to back into them, that right orientation. And of course you want to hit them hard enough to hurt their car, so sufficient energy. So those are 2 important things that you need to have happen. Quite often we look at the progress curve as this. So far with the previous unit, we just looked at what reactants we're at and what products we're at. Now we have a little curve to overcome. And that is referred to as the activated, where the activated complex is. So if I have, if I look at that example dealing with hydrogen and oxygen coming together, they come together, form this big short-lived super molecule, and then that could either go back and form the reactants again or go ahead and form products, which in our case up above was water. So the short-lived, unstable arrangement of atoms that may form products or form reactants is called the activated complex. So that is a transition state between reactants and products. Not reactant, not product, it's kind of the transition in between. And I kind of use a Star Trek analogy. When a member goes to beam out into another planet, they go into a special area where their molecules broke down and they get reformed on the planet. So that's kind of a transition state between the ship and the planet. Similar to over here, the supermolecule is a transition between reactant and product. Even if 2 molecules collide the right way, they may not form products. Why? Again, there's 2 requirements: correct orientation and sufficient energy. So you have to have enough energy. And I kind of asked the same darn question here again. Summarize the 3 statements of collision theory. They must collide, right orientation, sufficient energy. So those always come into play there with collision theory. Okay, so we have a few more pages here, a couple of diagrams. Likely won't be able to do it all in this one video, so I think what I'll do is I'll stop there, and we'll continue on starting off with activation energy. So we'll see you soon.